this talk, I will introduce my research, enhancing port localizers by leveraging project-specific fault patterns. This research is a joint work with Minseok Jeon, Hakjoo from Korea University, and Doha Hwang from Samsung Electronics. First, let me briefly go over the general process of software debugging. When a bug occurs in a program, developer first analyze the cause and identify the location of the fault. Then, they fix the fault and verify whether the bug has disappeared. As you can see, identifying fault is the very first step for the debugging. So this is where fault localization comes in. It is a technique that automatically identifies fault locations to assist developers in debugging. Given a buggy programming containing fault statement and a test suite with failing test cases and passing test cases, a fault localizer ranks the statements by how suspicious they are and provides the ranking to developers. The goal of fault localization is to place the correct fault location at a higher rank to reduce debugging effort. As shown in this example, if the fault localizer successfully finds the exact fault location at line 2, the developer can review it first and fix the bug quickly. And so the question is, how can we effectively find the correct fault location? To answer this question, we conducted an observation study on faults from the real-world software project. For example, Xzip2 is a utility library for reading, writing, and modifying image metadata. And we found that most faults occurred in Xzip2 are due to the input image metadata being incorrectly validated. This makes sense since the key feature of the project itself is to handle image metadata. So let's look at faults from the different versions of Xzip2. In the first version, there was a missing logic that validates the size of input data. And also similarly, in the fifth version, there are similar fault occurred again. The developer missed validating the size of the input data. So you can see that a similar fault pattern repeats across versions. In both cases, the variable big endian that indicates the byte order is used during the initialization, and fault statements involve a comparison operator to validate the initialized data. So our key observation is that such synthetically similar fault patterns are repeated across different versions. As mentioned earlier, this naturally happens because each software project has its own features designed for specific purposes. Now let's move to another cases. CPP check, a static analyzer for C++. As you know, C++ is a complex language with tons of synthetic features, so CPP check often struggle with pattern matching of tokens in C++ source code. As a result, most of its faults are caused by incorrect token pattern matching. So when we compare two versions of CPP check, we can see that the pattern matching statement for the variable name tok were incomplete. So through this observation, we found that each software project has its own unique and recurring fault patterns. However, existing fault localization techniques do not leverage such project-specific fault patterns. Instead, they attempt to apply a well-designed heuristic or a globally trained fault localizer to all projects. To overcome this limitation, we propose a new approach called project-aware fault localization. Our goal is to use a fault localizer that is specialized for each project's fault patterns. To achieve this, we introduced a new post-processing technique designed for project-aware port localization called PAFL. Our technique enhances a baseline port localizers by giving higher ranking to the statements that are similar to the port patterns. In this way, PAFL enables existing localizers to produce a ranking that considers project-specific port patterns. Now let me briefly explain the overview of PAFL. PAFL is based on two key ideas. The first key idea is to define a domain-specific language called crossword that describes the port patterns. So if a statement is described by this crossword, we increase its suspiciousness score so that it placed higher in the suspiciousness ranking. The second key idea is an algorithm that synthesizes port patterns. This algorithm analyzes past version of the target project and finds port patterns that can improve the ranking of port statements in the current version. To apply these key ideas, we first learn a baseline port localizer and represent the program source code as a special graph structure called an aggregated AST. Okay, first, the baseline port localizer is used to initialize the suspiciousness score for each statement. As you can see, the higher the score, the higher the ranking, the higher the statement is ranking. Now let me briefly explain the aggregated AST. Aggregated AST is a data structure that abstracts a full abstract syntax tree at the statement level. Each node represents a statement and is represented as a set of tokens, a set containing all tokens that belong to the statement. We specially designed the aggregated AST to represent the relationship between statements. There are two types of relationship. First, the sequential relation, shown as red edges, and second, the hierarchical relation, shown as blue edges. In this example, the third statement is a part of the second if statement, so they are hierarchically connected, and the fifth statement follows the second statement, so they are sequentially connected. Here, since each node corresponds to a statement in a program, we can map the suspiciousness score of the statement onto the corresponding nodes. Now, with the aggregated AST, where scores are mapped, PAFL updates the suspiciousness score of each node by applying the crossword. So let me explain how the suspiciousness scores are updated using a crossword. A crossword consists of a central node which represents the port statement, and 4 adjacent nodes that represent the context of the port statement. For example, this crossword describes a port pattern where the parent statement contains the variable x. The port statement is an if statement that includes a greater than operator, and the next statement is a return statement. Now we apply the crossword to every statement to update their suspiciousness scores. The method is quite simple. If a token that is included in the crossword is also included in a statement, we edit the mapped value of that token to the statement's original score. For instance, since the first statement has no matching tokens, its score remains unchanged. But for the second statement, the token if, so there is a token if, so add 0.3. The parent statement contains token x, so add 0.1. And the next statement contains return, which adds 0.2. In total, 0.5 is added to its original score. So when we apply the example crossword to all remaining statements, the port statement ends up with the highest score of 1.08. So As you can see, therefore, synthesizing such high-quality crossword is an essential step in the PAFL workflow. The synthesis algorithm consists of two main steps. The first step is to generate error embeddings to represent what failure looks like. An error embedding is constructed from the set of tokens covered by passing and failing test cases. In this example, the failing test case covers lines 1, 2, and 5. Thus, the covered tokens consist of two integer tokens, one apps token, and three x tokens, and so on. The second step is to select past version that are expected to have similar faults to the current version and synthesize fault patterns from them. PAFL computes the similarity between the current version's error embedding and those of past versions to select relevant version. Finally, it synthesizes fault patterns from the fault statements of the selected versions and applies them to the baseline fault localizer. Now let's move on to our experiments. To evaluate PAFL, we use 12 open source software projects written in Python and C++, along with various baseline fault localization techniques such as OOPSLA or LLM technique. We evaluated PAFL from two terms, effectiveness and robustness. First, PAFL effectively improves existing fault localizers across various scenarios. This table shows the performance improvement for spectrum-based fault localization techniques, which are the most widely used fault localization method. For instance, when using OOPSLA as the baseline, PAFL correctly links the fault statement at top 1 twice more often than the baseline. And second, performance degradation rarely occurs when applying PAFL. This graph shows whether the ranking improved or degraded after applying PAFL for each project. As shown in these graphs, PAFL performs robustly across most versions without significant performance drops. An interesting point is that even in projects like Spacey, where most versions do not share similar faults, PAFL synthesis algorithm successfully avoids selecting irrelevant past versions. In summary, we found that software projects often suffer from recurring fault patterns unique to each project. Based on this observation, we propose PAFL, a new fault localization approach that leverages project-specific fault patterns. The first key idea is to define domain-specific language that describe diverse fault patterns. And the second key idea is to synthesize fault pattern from past version that improves the ranking of current fault. Our evaluation result shows that PAFL enhances the existing fault localizers effectively and robustly across a variety of scenarios. And that brings me to the end of my talk. Thank you for listening.
We have time for a very quick question.
I have a question. If there are many lines which have bugs, can the method of ranking the lines work?
Sorry, could you ask me again?
I mean, your method rank the different lines and check the highest one. So when there are many lines which all have bugs, can it work?
So you mean that our metric is report the highest ranking, and so if when there are multiple fault statements, how this